This video is going to cover chapter 7, sections 1, 2, and 3. So we start with the angles of polygons in section 1 and the parts of polygons. So each segment that forms a polygon is called the side of the polygon. The common endpoint of the two sides is the vertex of the polygon, and the segment that connects any two non-consecutive, which means not one after the other, non-consecutive vertices is a diagonal. So in this diagram, the vertices would be A, B, C, D, and E. The sides would be AE, AB, BC, CD, and DA. And the diagonals could be something like BD. It could be BE, because those would be non-consecutive. A can go to D, A can go to C. Those would be non-consecutive. And then C can go to E and C. Oh, we already did C to A. Those would be all of your diagonals. The names of polygons are something that you need to know. If it has 3 sides, it's a triangle, 4 quadrilateral, 5 pentagon, 6 hexagon, 7 heptagon, 8 octagon, 9 nonagon, 10 decagon, 12 dodecagon, and anything else would be the number of sides / gon. So an 11 gon, 13 gon, 25 gon, anything like that. The first formula that we're going to learn about is the sum of the interior angles. So this is the explanation of it. To find the sum of the interior angle measures of a convex polygon, you can draw all the possible diagonals from one vertex of a polygon. In doing so, it creates a set of triangles. And then the sum of the angle measures of all the triangles would be the sum of the angle measures of the polygon. So for example, if I looked at the pentagon, if I picked one vertex, just one, and I drew all the possible diagonals, it would divide this into 3 triangles. Each of those triangles adding up to 180, so it would be 3 times 180. If you did a quadrilateral, there would be 2 triangles. If you did a hexagon, there would be 1, 2, 3, 4 triangles. So the pattern there is that there are 2 less than there are sides, which is where the equation comes from. N minus 2 times 180. So this just shows that pattern. If it's 3, there's 1 triangle, it would be 180. If there's 4 sides, it would be 2 triangles, it would be 360. And 5 and 3 would be 540. 6 and 4 would be 720. Now you don't have to memorize that because this formula, which is also on the next slide, is basically what you're using. N minus 2 times 180, where N is the number of sides. Here it is. The Polygon interior angles theorem is just a formula. And it says that the sum of the measures of the interior angles, and that's important because we're going to talk about exterior in a little bit, of a convex n-gon is N minus 2 times 180, where N is the number of sides. The corollary to that is the Polygon interior angles theorem, or the corollary to it. And it says the sum of the measures of the interior angles of a quadrilateral is 360. This is just because we use quadrilaterals a lot. So if I add up the 4 angles on the inside, that would be 360. If you use the formula, it'd be N minus 2 times 180, 4 minus 2 times 180, which is 360. Equilateral, equiangular, and regular polygons. So equilateral, just like a triangle, has all sides congruent. Equiangular, also like a triangle, all the angles are congruent. What's new is a regular polygon. And a regular polygon has all the sides and all the angles congruent. They are both equilateral and equiangular. So a square would be an example of a regular quadrilateral. All 4 sides are the same, all 4 angles are the same. Example 1 says classify the polygon by the number of sides and then tell whether it's equilateral, equiangular, or regular and explain. So if you look at A, you're going to count 1, 2, 3, 4, 5, 6 sides. There's 6 sides, so this is a hexagon. And all the sides have 1 tick mark, so they're all congruent. All the angles have 1 tick mark, so they're also all congruent, which means this is equilateral and equiangular or regular. B has 4 sides, so this is a quadrilateral. And the sides opposite each other are congruent, but not all 4, so it's not equilateral. And the angles opposite each other are congruent, but not all 4. So it's not equal angular either. So it's none. 6, or C, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. So this is a dodecagon. And the sides are all marked as congruent, which means it's equilateral. The interior angles, some of them are 90 degrees, but some of them are not, which means that it is just equilateral, not regular. All right, theorem 7.2 is the external angles theorem. So if I wanted to find the sum of the exterior angles of any convex polygon, one angle at each vertex, it's 360 degrees. So no formula here. No matter how many sides there is, if I took and added up all those exterior angles, it would add up to 360 degrees. All right, this takes your interior angle sum one step further to find the measure of each interior, and you can only do this if it's a regular polygon where they're all the same. So I take that sum, which is n minus 2 times 180, and I divide it by n. Again, n being the number of sides. All right, example 2 says find the sum of A interior and B exterior angles. Number 1 is a heptagon. This is 7 sides. So the sum of the interior would be n minus 2 times 180. 7 minus 2 times 180, which is 5 times 180. And 180 times 5 is 900 degrees. That's the sum of the interior. The sum of the exterior we don't have to do any work for because it is 360 no matter how many sides. 2 is a 17gon. 17 number of sides, so 17 minus 2 times 180. 15 times 180. I can do 180 times 15 and then bring down that 0. So bring down the 0, another 0, 7. This is 2,700 degrees for the sum of the interior, and the sum of the exterior, again, 360 degrees. All right, example 3 says find the number of sides of a convex polygon with the sum of the measure of the interior angles equal to 900. So this time we're looking for the number of sides. We're actually trying to find n. And we have the sum of the measure of the interior angles. So we have the n minus 2 times 180 part. It's equal to 900 degrees. What we don't have is the n. So if we're going to solve for n here, I'm going to take and distribute that 180. And I do 180n minus 360 equals 900. Add the 360. And divide by 180. So I can actually cancel through the zeros, and then I have 126 divided by 18. This would be 7 and 126. So n is 7. And you can always check by plugging it back in. If I did n minus 2, it would be 5 times 180. And that's our 900. All right, example 4 says find the measure of each interior and each exterior angle of the given polygon. So now each interior is what you're trying to find. This is your n minus 2 times 180 over n. And since the sum of the exterior angles are 360, each exterior would be 360 divided by n. Notice they all have to be regular. Otherwise, they're not all going to be the same. So if it's a quadrilateral, n is 4. So I'd get 4 minus 2 times 180 over 4. 2 times 180 over 4. And you can either multiply out the top and then divide it back into it. Or I could have simplified. Like I could have done 2 into 4 is 2 times 2 into 180 is 90. I could have done it that way. Or you could just straight up multiply and then divide. But this is the sum of the, or this is each interior. Each exterior would be 360 divided by the number of sides, which is also 90 degrees. The quadrilateral is the only one where that happens, that it's the same for both, so don't think that that's a common thing. All right, an octagon, our n is 8. So 8 minus 2 times 180 over 8, and I get 6 times 180 over 8. If you multiply it out, 180 times 6, you get 1080 over 8. That's once, 3 times, 5 times, 135 degrees. And then 360 divided by 8. Which is 45 degrees. And a regular 15 gone. So this would be 15 minus 2 times 180 over 15. This is 13 times 180 over 15. So I can either multiply out that 13, but this time let's try to reduce it. So I know that 5 goes into both 180 and 15. 5 would go into here 3 times, and 5 would go into here 36 times. And then 3 goes in here once, and this 12 times. So now I'm doing 13 times 12. Or 156. And then 360 divided by 15. Again, we can do 360s. These are both divisible by 5. So this would be 3. Or I can actually do, they're both divisible by 3, and I can do 5 and 120. And then 120 is 24 degrees. So any way that you can make that easier to simplify, I would recommend it. If not, you're just multiplying straight across. All right, chapter 7, section 2 is properties of parallelograms. So now we're going to get specifically into a quadrilateral that's called a parallelogram and learn all about its properties. So a parallelogram is a quadrilateral with 2 pairs of parallel sides. So in this diagram, you'll see that these 2 are parallel and these 2 are parallel. So quadrilateral, 4 sides, and 2 pairs of the opposite sides have to be parallel, or both pairs of opposite sides. To write the name of the parallelogram, you can use a little symbol that looks like a little mini parallelogram. You could use the whole word, like parallelogram ABCD, or you can use the symbol. In this diagram, AB is parallel to CD, and BC is parallel to DA. Here are theorems. So the theorems are really just properties. The first one is called the parallelogram opposite side theorem, and it says if a quadrilateral is a parallelogram, then its opposite sides are congruent. So not only are they parallel, but they are also congruent. AB would be congruent to CD, and BC would be congruent to AD. The next one is the parallelogram opposite angles theorem. And it says, if a quadrilateral is a parallelogram, then its opposite angles are congruent. So angle B is congruent to angle D, and angle C is congruent to angle A. Opposite angles congruent. 7.5 is the parallelogram consecutive angles theorem. And it says, if a quadrilateral is a parallelogram, then its consecutive angles are supplementary. So A and B would be supplementary. B and C would be supplementary, C and D would be supplementary, and D and A would be supplementary. Now this should make sense because if these are parallel lines and this is a transversal, B and C are your same side interior or consecutive interior, which would make them supplementary. And then if I rotate it around, C and D have the same relationship, D and A have the same relationship, and A and B have the same relationship. The next one is the parallelogram diagonals theorem, and it says if a quadrilateral is a parallelogram, then its diagonals bisect each other. So there's really 5 properties we know about parallelograms, including its definition. Opposite sides are parallel. Then we get into opposite sides are congruent. Opposite angles are congruent. The consecutive angles are supplementary, and the diagonals bisect each other. So I know all that information as soon as I see the word parallelogram. A, B, C, D is a parallelogram. Name all the pairs of parallel lines. So AB is parallel to CD, and BC is parallel to AD. 2 says name all the pairs of congruent angles. So not only do you have the opposite angles, like angle BAD equals angle BCD, and the others the other way. Angle CBA would equal angle CDA. You also have, and we're not going to list them all because it would take a while, but you also have vertical angles here. These 2 are congruent. These 2 are congruent. And because you have parallel sides, you have alternate interior angles. This matches this one. This one matches this one. And on the other transversal as well, this would match this one. And this would match this one. So all of those angles are congruent. 3 says name all the pairs of congruent segments. So we know opposite sides are congruent. BC would equal AD, and AB would equal CD. And we know that diagonals bisect each other. So BE is congruent to ED, and AE is congruent to EC. Example 2 says RSTU is a parallelogram, and then we're going to find all the missing values, X, Y, A, and B. So if we look at A first, X is opposite the 80, so X is 80 degrees. X and Y, or 80 and Y, are consecutive. They're going to be supplementary, which means Y is 100 degrees. And then opposite sides are congruent, which means B is 9. If there was an A down here, A would be 6. Go to B. The opposite sides are congruent, so A is 12. The diagonals bisect each other, so B is 9. X is this angle here. Y is this angle here. So Y and 45 are alternate interior, which means those would be congruent. Sorry, X is this whole angle here. And that angle with this angle would be supplementary. So if I add the 45 and the 35, I get 80, which means X, that whole angle there, is 100 degrees. And C, opposite sides are congruent, so 4x equals 8 and x equals 2. And these sides are also congruent. 3y plus 4 would equal 13. 3y equals 9. And y equals 3. Example 3 says find the perimeter of parallelogram PINE. It doesn't matter where I put the P as long as I go in order after that. And I could go clockwise or counterclockwise. But PI is 12 and IN is 8. So the opposite sides would be the same. And the perimeter, I would add up all those sides. So 12 plus 8 is 20. 12 plus 8 is another 20, which means the perimeter is 40. Example 4, and we're back to the proofs. So this says to write a 2-column proof, given A, B, C, D, and G, D, E, F are parallelograms. You want to prove that angle B is congruent to angle F. So I want to eventually get to link these two. Well, based on the fact that they are parallelograms, so I'm going to start there, A, B, C, D, and G, D, E, F are parallelograms. That's my given. I know that each of them has opposite angles that are congruent, and these two angles are congruent because they're vertical angles. So if I can link one to the other, I can use the transitive property to get to the other side. So I can say angle B is congruent to angle CDA. I have to use 3 letters there because D is shared. And that's the fact that parallelograms have opposite angles congruent, or the parallelogram opposite angles theorem is its name. If you want to just write out, if it's a parallelogram, opposite angles are congruent, that's fine too. And I can use the same reason for EDG and EFG, or angle F, because that one only has 1 letter. So I could put those together because they both have the same reason. So those would be have double tick marks. Then I can say angle CDA is congruent to angle EDG, and that's the vertical angles theorem. So if B equals D here and D equals EDG, then I can say B equals EDG, and I can use this in 2 statements. So I could say angle B is congruent to angle EDG, and that's transitive. And if B equals EDG and EDG equals F, then B also equals F. And that would also be transitive. Oh, step 5. Or I could have done, in place of those 2 transitive statements, I could have used substitution and gone directly from 3 to 5. Both would be completely right and earn full credit. All right, this one is our coordinate one. So I'm going to bring in a coordinate grid. And it says W, X, Y, Z, or the vertices of are -1, -3. That's W. X, -3, +2. And Z, 4, -4. And I need to find Y. So I know it goes W, X, which means Y has to go in this section here, then Z. So this connects to this connects to this. And because they're parallel, the easiest thing to do is find the slope of XZ and count up, or sorry, XY, and count up from Z that slope. So this is a rise of 1, 2, 3, 4, 5. We're going up 5 and then to the left 2. If I do the same thing from Z, up 1, 2, 3, 4, 5, and over 2, there's Y. And the coordinates of Y are 2, 1. You could have also found the slope of WZ and counted it from X. So that's down 1 and to the right 1, 2, 3, 4, 5. So if I went down 1 and right 1, 2, 3, 4, 5, I get that same coordinate. All right, last one in this video is 7.3, which is proving that quadrilateral is parallelogram, which is basically the converses of 7.2. In 7.2, we said if it's a parallelogram, here's all the properties, which were opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, diagonals bisect each other, and by definition, opposite sides are parallel. Now we're using those things to prove that a quadrilateral is a parallelogram. So the first theorem is the parallelogram, opposite sides, converse. Again, we're doing the converse because we're flip-flopping. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. We'll notice every time these end, then a quadrilateral is a parallelogram because that's what we're proving. So if this is congruent to this and this is congruent to this, then I can say A, B, C, D is a parallelogram. Next up is parallelogram, opposite angles, converse. Again, converse being the operative word because we're proving that it's a parallelogram. If both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. I've got both pairs of my opposite angles marked as congruent, so this is a parallelogram. Next up, opposite sides, parallel and congruent theorem. So this one's a little different because we didn't have this individually before. You only need one pair, but if one pair of opposite sides are both congruent and parallel, then the quadrilateral is a parallelogram. So in this diagram, we only have one pair marked up, but it is both parallel and congruent. That's enough information to prove this is a parallelogram. The parallelogram diagonals, converse, says if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So this is congruent to this, and this is congruent to this, showing that those diagonals are bisected. So then this is a parallelogram. So there are 5 ways to prove a quadrilateral is a parallelogram. The first one is by its definition, if both pairs of opposite sides are parallel. So if I use this statement in a proof, I can simply write the definition of a parallelogram. If both pairs of opposite sides are congruent, this is opposite sides, converse, parallelogram, opposite sides, converse. The third one is show one pair of sides are congruent and parallel. And this is opposite sides, congruent and parallel theorem. This is not the converse because this is the one that's new. The fourth one, both pairs of opposite angles are congruent. This would be parallelogram, opposite angles, converse. And diagonals bisect each other, parallelogram, diagonals, converse. So any one of these 5 ways would prove a quadrilateral is a parallelogram. This is just giving you the visual. So both pairs of opposite sides, that's the definition. Both pairs of opposite sides, both pairs of opposite angles, one pair opposite sides, congruent and parallel, and diagonals bisected. Remember that the numbers are not as important as the name. So if you're going to use the theorem, you need to give the name or just describe what it says. All right. Example 1 says state the principal definition or theorem that enables you to deduce from the given info that the quadrilateral is a parallelogram. So we've got the picture here. Number 1 says BE equals ED and CE equals EA. So these are our diagonals. This is the parallelogram, diagonal, converse. It says if both pairs of diagonals are bisected, then the parallelogram is congruent. Then the quadrilateral is a parallelogram. Next up, angle BAD is congruent to angle DCB, and ADC is congruent to CBA. So this is the opposite angles. Parallelogram, opposite angles, converse. 3, BC is parallel to AD and AB is parallel to DC. This is the definition of a parallelogram. 4, BC is equal to AD and AB is equal to DC. That's opposite sides. And the last one, BC is parallel to AD and BC is equal to AD. So this is the only one that's not the converse or the definition because this is the new one. Opposite sides, congruent, and parallel theorem. All right, example 2. For what values of x and y is your quadrilateral PQRS a parallelogram? So in order for these to be a parallelogram, the opposite sides have to be congruent. So x plus 9 would have to equal 2x minus 1, and y would have to equal x plus 7. The bottom one has 2 unknowns, so I have to use the top first. Subtract the x. Add the 1, and x is 10. Then take and plug that in. Y would equal 10 plus 7, and y is 17. Example 3, for what values are x and y makes the quadrilateral a parallelogram. Now we're dealing with the angles. Opposite angles would be congruent. So 3x minus 32 would equal 2x. And 4y would equal y plus 87. This time it doesn't matter which one we solve first. So if I were to subtract the 3x, I get negative 32 equals negative x, multiply or divide by negative 1, and x equals 32. Subtract the y here, 3y would equal 87. Divide both sides by 3. 87 divided by 3 is 29. And last up, our two-column proof. Given angle ADB is congruent to CBA, so ADB is this angle here, congruent to CBA, this angle here, or CBD, sorry, and ABD is congruent to CDB. Prove the the quadrilateral is a parallelogram. So I am given that these are actually alternate interior angles, right? Those are congruent. So I can use that whole given. If that's the case, so if I have two lines here and this transversal and this angle is congruent to this angle, then I can say AB is parallel to DC, and that's the alternate interior angles converse. And then if I use these sides and this transversal and this angle are congruent, then I can say AD is parallel to BC. Same reason, alternate interior angles converse. And if both pairs of opposite sides are parallel, then ABCD is a parallelogram. And my reason is the definition of parallelograms. Now, you could have also, completely different, but I could have also proved this side was congruent to itself using reflexive. Then I could have proved these two triangles were congruent using angle, side, angle. And if the triangles are congruent, their corresponding parts are congruent. So I could have said this one equals this one and this equals this one. And that would have been CPCTC. So that would have started with the given. I would have done DB equals DB, and that's reflexive. I would have said triangle ABD is congruent to triangle CDB, actually CBD, and that's angle, side, angle. Then I could have said AB equals DC and AD equals BC, and that's CPCT, C. Then ABCD is a parallelogram, and my reason is the opposite parallelogram, opposite angles converse. So two completely different ways, but they're both right. That wraps up 7-1 to 7-3. Have a great day.